Lesson: Case Studies and Applications. Artificial intelligence has become a pivotal component in enhancing cybersecurity measures, particularly in the implementation of intrusion detection systems. The integration of AI into IDS has revolutionized the ability to detect, analyze, and mitigate cyber threats in real time. This lesson delves into the case studies and applications of AI in IDS, providing a comprehensive understanding of how theoretical foundations translate into practical, effective cybersecurity solutions. One notable case study is the application of machine learning algorithms in the IDS employed by a large financial institution. Financial institutions are prime targets for cyber attacks due to the sensitive nature of the data they handle. In this case, the institution implemented a combination of supervised and unsupervised machine learning techniques to enhance their IDS. Supervised learning algorithms were trained on labeled datasets comprising known attack patterns and benign network traffic. This training enabled the system to accurately identify and flag known threats. On the other hand, unsupervised learning algorithms were utilized to detect anomalies in real-time network traffic, identifying potential zero-day exploits and previously unknown attack vectors. The implementation of these AI-driven techniques resulted in a significant reduction in the time required to detect and respond to cyber threats, enhancing the overall security posture of the institution. Another compelling application of AI in IDS is seen in cloud computing environments. Cloud services are increasingly becoming targets for cyber attacks due to their widespread adoption and the vast amount of data they host. AI-driven IDS in cloud environments leverage deep learning techniques, particularly neural networks, to analyze immense volumes of data and identify subtle deviations indicative of malicious activity. For instance, a study demonstrated the effectiveness of using convolutional neural networks to detect distributed denial-of-service attacks in cloud environments. The CNN-based IDS was trained on a dataset of network traffic and was able to achieve an accuracy rate of 98.7% in detecting DDoS attacks, significantly outperforming traditional IDS methods. This case study underscores the potential of deep learning techniques in enhancing the detection capabilities of IDS in dynamic and complex environments like cloud computing. The healthcare sector also provides a pertinent example of AI applications in IDS. Healthcare organizations are increasingly targeted by cybercriminals due to the high value of medical records and personal health information. An AI-driven IDS was implemented in a large healthcare provider network using a hybrid approach that combined rule-based systems with machine learning algorithms. The rule-based component was designed to detect known threats based on predefined signatures and patterns, while the machine learning component focused on identifying anomalies and potential threats not covered by the rule-based system. This hybrid IDS was able to detect 96% of known threats and 92% of unknown threats, demonstrating the effectiveness of combining traditional and AI-driven techniques in a comprehensive IDS solution. In addition to sector-specific applications, AI-driven IDS have also been employed in critical infrastructure protection. Critical infrastructure, such as power grids and transportation systems, is increasingly being targeted by sophisticated cyber attacks. A case study involving the implementation of an AI-driven IDS in a smart grid environment illustrates the potential of AI in protecting critical infrastructure. The IDS utilized a combination of support vector machines and genetic algorithms to analyze network traffic and detect anomalies indicative of cyber attacks. The system achieved a detection accuracy of 95% and was able to significantly reduce the false positive rate compared to traditional IDS methods. This application highlights the importance of AI in enhancing the resilience of critical infrastructure against cyber threats. The integration of AI into IDS is not without its challenges. One of the primary challenges is the need for large and diverse datasets to train machine learning models effectively. The performance of AI-driven IDS is heavily dependent on the quality and representativeness of the training data. Inadequate or biased datasets can lead to poor detection accuracy and high false positive rates. Additionally, the dynamic nature of cyber threats necessitates continuous updating and retraining of AI models to maintain their effectiveness. Despite these challenges, the benefits of AI-driven IDS in terms of improved detection capabilities and reduced response times are undeniable. The future of AI in IDS looks promising, with ongoing research and development aimed at addressing current limitations and enhancing capabilities. One area of focus is the development of explainable AI techniques that provide greater transparency and interpretability of AI-driven IDS decisions. This is crucial for building trust and ensuring that cybersecurity professionals can understand and act on the outputs of AI systems. Additionally, advancements in federated learning and edge computing are expected to further enhance the scalability and efficiency of AI-driven IDS, enabling real-time threat detection and response across distributed networks. In conclusion, the application of AI in intrusion detection systems has proven to be a game-changer in the field of cybersecurity. Through various case studies across different sectors, it is evident that AI-driven IDS offer significant advantages in terms of improved detection accuracy, reduced response times, and enhanced overall security. The challenges associated with AI integration, such as the need for quality datasets and continuous model updates, are being actively addressed through ongoing research and development. As AI technologies continue to evolve, the capabilities of IDS will undoubtedly be further enhanced, providing robust protection against an ever-increasing array of cyber threats.